All right, we're going to look at the math of circular motion. In the conceptual videos, you learned that things go in circles because there's a force acting on them pointed towards the center of the circle, and we call that a centripetal force. When things move in circles, they accelerate. We learned a long time ago that the change in velocity over time is the acceleration, and I said it would be very important at some point to understand that velocity is a combination of speed and direction, and that you could change something's velocity by just changing its direction. So if we have something moving in a circle at a constant speed, it is accelerating. And that centripetal acceleration, we put a little C for centripetal, which is pointed towards the center of the circle as well, because the acceleration is always in the direction of the net force, can be calculated by taking the linear speed of the object and dividing it by the radius of the circle it's traveling in. I'm not going to go into where this formula comes from, but there it is. Now, if I take that and use F equals ma on it, that means that the centripetal force equals the mass times the centripetal acceleration. And since centripetal acceleration is v squared over r, we get this lovely equation, which you can just see is the mass times the centripetal acceleration. Now, how do I apply this? Any problem where you have something moving in a circle, you're going to need to use this formula. We're going to use it in the exact same way that we used Newton's second law before. We're going to draw free body diagrams and use the free body diagrams to help us out. Now, simple problems have something going in a circle, and you just have to identify what force is pointing towards the center of the circle. So let's say, for instance, I have a ball on a string, and I'm swinging around in a circle, and here's my ball, and it's going around in a circle. I'm going to make it a small circle, something like that. Here's the center of the circle, and there's something pointing towards the center of the circle. Well, if it's a ball on a string, that's tension. Since the tension is the force that points towards the center of the circle, it is the centripetal force. One of the things you have to understand about centripetal force is it's not a new force, it's a job. It's a job that any of the forces that we know so far, weight, tension, friction, normal force, can perform. The tension is the force that's making it go in the circle. It's fulfilling that role. So when I make a substitution into this formula up here, I'm going to replace the net force centripetal with tension. And I wind up with this equation. What would be another situation? How about a situation where friction makes something go around in a circle? Now, when you have something like a car that goes around in a circle, I tend to do the free body diagram as if the car was going away from me or towards me. And then I would assume that the center of the circle is over here somewhere. And there's a reason for this, because this car is going to be using friction to go around the circle, but it's also going to have a normal force and weight. And I need a way to be able to get that into my free body diagram, which means that I have to draw it from this point of view. If I drew it from the top, it'd be kind of hard to see where the normal force and the weight are. Now, looking at this free body diagram, I could come up with two equations. I could say, first of all, the net force pointing towards the center of the circle, aka the friction force, is my centripetal force. And so I would take this and substitute in mu Fn for the centripetal force equals mv squared over r. But I also have two forces that are pointed, one up and one down. And I'm going to use Newton's second law for that, and I'm going to substitute for the left-hand side the up force minus the down force, normal force minus mg equals ma. And since this car is only accelerating towards the center of the circle, that acceleration in that direction is 0, which means that the normal force equals the weight. And then I could substitute that into this other formula, something like this, like we kind of have a tendency to do whenever we have the normal force. And I get mu mg equals mv squared over r, and you can see that the mass doesn't even matter. And I can solve for any of these variables now that I have this basic equation that I've derived by drawing a good free body diagram of the situation. Now, that's an example of friction being a centripetal force. What about the normal force? Can the normal force be a centripetal force? Of course it can. Let's think about when you put clothes in the washer and you put it in and it starts spinning around in the spin cycle, and you've got clothes attached to the insides of the cylinder, and if they're moving around in a circle, then, and by the way, I'm looking down from the top, like we're looking down into the washer, and that means that there must be some force pointing towards the center of the circle for each one of these objects that is making it go in a circle. And since it's the side of the cylinder that's pushing on it, that anytime a surface pushes on something, that's a normal force. And so now my normal force is my centripetal force. And so when I substitute into centripetal force equals mv squared over r, I'm going to write normal force equals mv squared over r. So what we've seen is that tension can make things go in circles, friction can make things go in circles, normal force can make things go in circles. So they can all act as a centripetal force. The fourth force that we learned about, gravity, can also make things go in circles. We're going to save that one until we study universal gravity in the next section, because that's how we analyze satellite motion, because the gravity between the Earth and a satellite is what makes that satellite circle the Earth, and we can actually even apply this stuff to that. But we're going to hold off on that because that's a little bit more complicated. And that'll do it for this particular video.